Hello everybody, welcome back. My name is Michael. Thanks so much for joining me today. Today we're going to be jumping back into Harvard CS50X 2025 Lecture 5 on data structures. This is week 5 of Harvard CS50X. Let's jump on in.
This is CS50, and this is already week 5. This is our last week on C, and it's also reputed generally to be the most challenging, perhaps, of weeks whereby we sort of climax with the material we've been exploring thus far. Sort of metaphorically, it's like we've been going up this hill, and I know it's felt like a lift each and every step, but now things kind of plateau out, I dare say. And even though it's not going to feel like we're suddenly going downhill or things get markedly easy, I do think you'll be able to catch your breath and start to apply a lot of the lessons learned over the past few weeks to everything that lies ahead. And among the things that lie ahead are exactly these, data structures, which we've only touched on briefly so far. We had this look at arrays way back in week 2 already, and we've used those in a few different ways. But arrays are a super simple data structure. Data structure meaning it's a way to structure your data in the computer's memory, insofar as they have to be generally the same data type, but most importantly, back to back to back. And the catch with arrays, recall, is that you have to decide in advance how big the array is going to be. Do you want size 3? Do you want size 30, 300? But you do indeed have to decide in advance. But there's other things in life, not only the virtual world, but the real world, that we might consider a bit more abstractly. And in fact, you're going to start to notice after today, ideally, that the world is filled also with abstract data types, whereby these ways of structuring information, but that don't depend necessarily on the underlying implementation details. That is to say, you can implement certain features in life, in code, but there's bunches of different ways to actually implement them at a lower level, whether it's using arrays or, in fact, as we'll see today, other data structures as well. So while data structures are something very concrete, involving variables and pointers and functions and the like, abstract data types are a little more broadly descriptive. For instance, there are in the world these things called queues. Turns out there's things in the computer world called queues too, but in the real world, a queue is like what? Where might you see queues in the real world?
A line.
Definitely in the UK, because they're typically called this there. So, like a line at a movie theater, like lining up for dinner or lunch or any kind of line, you have queues. Now, queues have some kind of ordering, often of people, but certainly in the virtual world, you might have queues as well. In fact, this isn't as common nomenclature anymore, but if you're printing a bunch of things to a printer, those documents are generally stored in a queue so that they all print out in that precise order. And we can actually see this in the real world. So we wonderfully have 3 brave volunteers, if you 3 wouldn't mind coming on up. These guys have formed what I would argue is a queue. They've sort of lined up wonderfully in order to receive their sort of thank you prizes. So in fact, if I hand these out in the order in which they kindly volunteered, we have 1 thank you here, thanks very much. We have 2 thank yous here, thank you very much, and 3 thank yous. Maybe a round of applause for how easy that was for our volunteers. So it's sort of
They're just like
equitable
us.
all around. And notice that the queue actually, if we kind of geek out about this, actually had some operations associated with it. And I dare say we could somehow implement it in code as well. So a queue, or a line in the real world as we know it, is actually an example of a FIFO data type. First in, first out. So that's sort of a property of this structure, no matter how you implement it, that describes sort of the equity of how you put the data in and get it out, or in this case, the human volunteers. The first one to line up at the front there, Akshay, got his prize first because he was indeed first in line, and then the second person and the third person. So not all that interesting. You would kind of hope or expect that that's how life works when people line up or queue. But let's make this now a little more granular in the world of coding. So if you were to implement that same structure in code, be it for a printer or some kind of Ticketmaster type scenario where you want to ensure a FIFO property, you would generally have 2 functions or 2 fundamental operations. NQ, which means to put someone into the queue, and DQ, which means the opposite, to take someone out. And just as FIFO implies, like the first in is the first one NQ'd, but they're also the first one out to be DQ'd. So just some terminology. Now, how could we make this in code? Well, if we suppose for the sake of discussion that you want to have a queue, like a line, that can fit 50 things or 50 people in total, a capacity of 50, we could declare an int and make it a const so it can't actually change and initialize that to 50. And then we could use that elsewhere in our code, and we could create our own structure using typedef as well that includes this many people in an array called exactly that, people, each one of whom is of type person. So recall from weeks past, we used the struct keyword already. We used the typedef keyword already to invent our own data type called person. So let's just assume for the moment that now exists. But notice that you can actually encapsulate data types inside of data types even if you've made both yourself. So the world starts to get more interesting when you structure things in this way. But I also have inside of this new struct, which indeed I'm going to call a queue in code, also size. Why is it that I need to keep track of the total capacity of a queue in code, but also apparently I constantly have to keep track of the size of the queue?
You have 50
it's a subtle
places,
difference,
but maybe you
but
don't
these
have
two words
50
mean something
elements.
very distinct.
You could have
capacity is and always
one
will be
element
50 because
in
it's a
the queue at
constant.
once, but you have 49 blank
size
spots, so your size would
is different
represent
how?
the amount of elements, not the length of
Just
the actual
intuitively,
array.
yeah. Yeah, so size is going to be the current number of people or things in the queue. And it stands to reason that you've got to keep track of both, because otherwise you might have like 50 garbage values in memory. If you want to keep track of how many of those values are valid and represent, in this case, persons or people, well, you need to know if there's 0 people there, or 1, or 49, or 50, or anywhere in between. So this is how we might, in code, and we won't go down this road further, how we might in C code implement the idea of a queue using familiar syntax by kind of layering some of these ideas we've seen already. All right, but it turns out you don't always want queues, and you specifically don't always want FIFO. So there also exist in the world these things called stacks. For instance, if playfully I propose that I actually do own different colored clothes. In fact, I've got like a red sweater, I've got a blue sweater, but if at home in my drawer or closet, I store all of my sweaters in literally a stack, like this one here, well, it stands to reason that if I'm doing sort of laundry frequently enough, I might wear this on Monday, this on Tuesday, this on Wednesday, then I might do a load of laundry, and so they're back on top of the stack, and I never actually get to the bottom of the stack here. So this is a very different operation. It's not equitable in the same way our queue was, because it would seem that the last sweater I put in is going to be the first sweater I take out. Now, this sort of stands to reason that that's obviously how the real world works when you stack clothes together. But these things called stacks are everywhere, too. Like in the dining hall, in Annenberg Hall, there's a whole bunch of trays, presumably. And unless the dining hall is really busy, there could be one really dirty, nasty tray at the very bottom of the stack that never gets used because people are constantly taking the ones higher up until they finally refresh them and clean them. In the world of technology, like your inbox, if you use Gmail, I mean, that's actually a stack in and of itself. Why? Because when you get new mails, where do they typically visually end up? Well, sort of at the top, at the top, at the top. And if you're like me, if you get lots of emails that you don't really necessarily get to all of them, you might reply to someone who wrote you most recently and completely blow off someone who wrote you earlier because they've been pushed further and further down, so to speak, in the stack. So these data structures, or these rather data types, are really everywhere. And stacks, therefore, suffice it to say, are not FIFO, first in, first out. They're what the world calls LIFO, last in, first out, because the last sweater into the stack is the first one that I actually pull back. And so we can see this even more clearly with 3 more volunteers. If you 3 wouldn't mind coming on up. These 3 have clearly stacked themselves into exactly this data structure, a stack, which is actually too bad because I only have like 2 prizes this time. So I think I can offer you your prize, and we can offer you your prize. And unfortunately, we can just give you a round of applause because you were the first one into the stack. OK. All right, we actually have a third, but point is hopefully made. So thank you to these 3 volunteers. That's all we needed you for. But a LIFO, then, is a data type that indeed has that property, which you might want in some contexts, like your Gmail inbox. You might kind of have to tolerate in the physical world just because of gravity and how closets and drawers work. But it isn't necessarily a property that you want of all data types, for instance. Case in point, in the world of printers, would be kind of obnoxious if a lot of people in an office or university are printing to a common shared printer, but only the person who printed most recently is the one that gets their document first. So you'll see in the real world not only queues, but potentially stacks, especially when things maybe get unfair when you're in a store and the cashier isn't necessarily honoring the first in, first out property. But as for operations, these 2 have some vernacular. And so instead of NQ and DQ, in the world of stacks, we actually generally say push, which means to push something on top of the stack, and pop, which means to remove something from the top of the stack. But top of the stack is the operative word. You're not sort of sliding the blue sweater out from under everything else. You're only operating at the top of the data structure. But it turns out if we think now about stacks as being this abstract idea that have these operations associated with them, in code, we could actually implement them pretty much the same. So notice here, the only difference on this screen here is that I'm calling this structure a stack, but the stack still has some capacity. It still has some size. But if you sort of imagine in your mind's eye how a stack differs in code from a queue, whatever loop you're using, whatever conditionals you're using, you're probably removing things from a stack from a different part of the array than you would from a queue. So if you just imagine, maybe you start removing things from the front instead of the back. At the end of the day, you can implement these abstract types using similar code here, but you're going to have to tweak the operations to give the property that you want FIFO or LIFO. So again, the overarching goal of just introducing stacks and queues at this point is that there is this distinction between an abstract data type, like some way of organizing information that has certain properties, certain operations, but you don't necessarily need to know or care how it's implemented in code, because clearly you can implement it one way or the other, and the actual data structures with which you are building those abstractions. So one's high level, one's low level. And indeed, that's the whole purpose of abstraction. So our friend Professor Shannon Duvall at Elon University actually brought this same idea to life with a short video in which Jack learns the facts about queues and stacks. So we thought we, for a moment, to hammer this home, would dim the lights and hit play on this short film. And queues are, let's actually transition now to building things and building on top of where we started in week 2 with arrays, and really reach a peak today of sophistication when it comes to using last week's concept, that of pointers, to kind of stitch together in a computer's memory really any kind of structure that we want. But recall first that arrays indeed had this key property that everything was contiguous, back to back to back. So for instance, if in week 2 onward, we wanted to store like 3 integers in memory, it might look abstractly a little something like this, where we might put 1 and 2 and 3. But the catch with arrays, recall, is that you have to decide in advance, as per those square brackets, like how big the thing is going to be. And so if you decide in advance with square brackets that you want an array of size 3, but later you realize, oh darn, I want to have a 4th integer or a 5th one, you might have actually metaphorically painted yourself into a corner. Ideally, you would put the number 4, for instance, right here. But again, in the context of the computer's whole memory per last week, there's other stuff going on. So for instance, these might not necessarily all be freely available to use, because if you've got 1, 2, 3, multiple variables and lots of functions in your program, well, these other memory locations might be filled with actual values and as well as garbage values. So as per Oscar the Grouch here, assume that anything with him just represents a garbage value, where sure, we can use that location in memory, but there might actually be valid strings like hello, comma, world, \0. And I've kind of grayed it out because it's separate from the 1, the 2, and the 3. But there could be another variable in your program that's storing hello world, and just by chance, because you created that variable after the array, you ended up with an H immediately after the 3. So it would seem that you've indeed painted yourself into this corner in that unless you sacrifice that H and wreck that whole string, there's no room for the 4. But is there? I mean, obviously, there's a lot of room for the number 4, not to mention the 1, the 2, and the 3, because all of those garbage values don't mean you have to respect them. You can reuse those locations. They're garbage in the sense that you use them already, but you're no longer using them. So I could put this 1, 2, 3, and 4 somewhere up here, somewhere here, maybe even somewhere down here. So how could I then accept the fact that I do want to grow this array? Well, I could just say, fine, I'm going to have to sort of bite my lip and just copy the 1, the 2, the 3 to a brand new location that actually has room for a 4th value as well. And we can put the 1, the 2, the 3, and we can now have room for the 4. And then we can get rid of the original array somehow. So this is a solvable problem, even though we haven't had to do it in code yet. But what's a downside of this solution to growing an array to store more data?
Slow n times. You have to copy
after you first create it.
O of n in the worst case.
It takes up more. Well, it takes up more space in a good way at the moment. I think it's not so much space that we're worried about here.
Come on. Show me.
Sorry? Yeah, you have to keep doing this again and again. So if I can put words in your mouth, it takes more time, because now just to insert one value like the number 4, instead of just jumping to a free location and putting it there in constant time, I kind of have to incur linear time to copy the original array into a slightly bigger array and then add that new 4th value. So you're just kind of wasting your own time. Now, there's a potential alternative. What could we do? Well, I could have just allocated more space than I need from the get-go. So even though I asked the compiler for 3 integers, maybe it could be a little generous and just give me 4 secretly, or 5, or 500, or heck, 5,000, so that I never deal with this problem in the future. That way, everything would be super fast because I never have to waste time moving things. But what would be the downside of that approach? Sort of over-allocating memory for an array.
You run out of memory, right?
So it's a waste of space. I mean, there's only a finite amount of memory in your Mac, your PC, your phone. Why are you going to write code that's sort of designed intentionally that way, but arguably poorly designed, because you're just throwing memory away that no one can actually use. None of your other programs or apps can actually use, because you just want to make sure you can grow this array in case you ever need it. So that too doesn't really feel like a compelling trade-off. But here is really a theme now that we'll see really throughout the semester and throughout computing. There's always going to be some trade-off, and it's very often between time and space. But as we've discussed in the past, it might be a trade-off between the complexity of your code. I mean, honestly, imagine in your mind the sort of for loop or the while loop that now you have to write code for to copy all of that from old to new array. Like, that's added complexity. We're wasting my human time. We're introducing more lines of code that increases, theoretically, the probability that one of them has a bug. So there's just lots of trade-offs of solving problems in this or really any other way. So what might we do? Well, what if we could structure our data a little more intelligently? Rather than just use this super simple data structure called an array, where everything has to be back and back and back, could we instead sort of treat the computer's memory kind of like a canvas, such that if there's free space over here, fine, I'm going to put something over here. If there's free space over here, fine, I'm going to put it over here. Can I just then stitch these things together somehow? And I'm using that word deliberately because last week we saw pointers, which are just addresses. But maybe I can sort of metaphorically, and as per the arrows I drew on the screen last week, maybe I can just kind of connect the locations in memory that are available so that I no longer need to care if my data is back to back to back in memory. I can just sort of follow arrows from one piece of data to another. And all we need for this is some mostly familiar syntax. One, we have struct, which is the keyword with which we can create a structure, our own data type, along with typedef. There's dot, which we haven't used that much, but we did see a while back, where by using the dot operator, you can go inside of a structure to get at the name or the number field, for instance, in a person. And then, of course, we spent last week really focused on the star operator, so the asterisk, whereby you can use pointers in some way. So using just these three, we can actually build most anything we want structurally in our computer's memory. And in fact, the only new piece of syntax today is going to be this, an arrow, which is just a hyphen and a greater than sign, which, as we'll see, is the exact same thing of using a period and a star together. We'll see what that means in just a bit. So how can we go about implementing an alternative to arrays that actually allows us to grow and even shrink them if we want, without having to move everything that already exists in memory around in some way? Well, let's see where we might begin with arrays alone. Let me go ahead and create a file called list.c. And in list.c, let's include standard io.h at the top. Let's declare int main with no command line arguments. And then let's super simply do int list3 to give myself an array called list of size 3. And then just for the sake of discussion, let's go ahead and put at the 0th location, that is the first, the number 1, at the location 1, the number 2, and at location 2, the number 3. So even though the array, recall, is 0 indexed, I'm going to use some human numbers like 1, 2, and 3 in sequence like this. And then let's just do something mildly interesting, like for int I equals 0, I less than 3, I plus plus. And then inside of my loop, let's just print out those numbers just to make sure that they are printing as I would expect. All right, so if I scroll up to the top of this code, there's not all that much going on other than I'm creating an array of size 3 with the numbers 1, 2, 3, and then I'm printing them out with a simple loop. All right, let's do make list. So far, so good. /list, and there we go. 1, 2, and 3. All right, so that works perfectly fine so far. But let's actually see what would be involved if we are using arrays alone to grow and shrink this array. So let me go back into my same program. Let me throw pretty much all of this away for the moment, and let me propose that we're going to create the array in a different way, in a way that we haven't done before. I'm going to say int star list equals the return value of malloc, whereby I want 3 times the size of an int. So I've not actually created, in class at least, an array in this way. But if an array is just a sequence of values, contiguous in memory, And malloc, we saw last week, is just a function that gives you a chunk of contiguous memory. I could kind of do things the old-fashioned way and use malloc to give myself a chunk of memory and then treat the first part of it as space for an int, the second part as space for another int, the third part as space for a third int. I'm just kind of doing things at a lower conceptual level. Of course, to use malloc, we needed to include last week standard lib.h, so that gives me access to that. And recall that sometimes things can go wrong. What does malloc return if there's no memory available anymore? Null. So null, two L's in the context of memory. So if this list value happens to equal null, well, there's nothing interesting to do here. Let's just return 1 and exit the program altogether. But if we don't have that error, let's assume that I did get back a chunk of memory that's big enough for 3 integers based on whatever their size is on the computer I'm using. So let's now initialize this array. List bracket 0 gets 1, list bracket 1 gets 2, and list bracket 2 gets 3. So just as before, I'm initializing it in the same way. But now, let's suppose that time passes, and I decide that, oh, darn it, I really wish I had allocated space for a 4th integer. Now, obviously, I can just change this code quickly. But let's assume that this is a much more complicated program. It's running all the time. And maybe it's up to the user to say when they are ready to give me a 4th integer. So this is a simplification. But at this point in my story, after some time has passed, let me propose that, oh, darn it, I've painted myself into that corner. Let's reallocate a new array that's a little bigger. Well, how can I do that? Well, let me go ahead and temporarily give myself a variable called temp, TMP for short, set that equal to the return value of malloc, whereby I'm asking now for 4 times the size of an int. So I'm just sort of changing my mind later on in this program. I actually want an array of size 4. OK, I still have to check that nothing went wrong. So if temp equals null, then let's go ahead and return 1. Then let me go ahead and copy everything from the old array into the new array. So how do I do that? Well, I can do for int I equals 0, I less than 3, I plus plus, just like I was printing the thing out earlier. And I can say put into the temporary array at location I whatever is in the original array at location I as well. So this is kind of like the string copying program we wrote last week, where I did everything manually by copying one into the other. Now I'm just doing it more generically for integers in 2 arrays. Then if I want to go ahead and add a 4th number to this array, I can literally do temp bracket 3 gets 4. And I'm saying gets to mean assignment here. And that's just adding now the 4th value to the array, just like I did a moment ago by plopping the 4 into the bigger chunk of memory. All right, I'm almost done here, but I do need to do some cleanup. After I have created this new array of size 4, I don't think I need the original array of size 3. So recall from last week, I can free the original list, and that just hands it back to the operating system. And then if I want to keep this new chunk of memory around, you know what? I'd rather call it list instead of temp. So because both of those are just variables, I can simply say list equals temp. And this just sort of renames that new bigger chunk of memory to be the actual list that I care about, so that moving forward in this program, I can continue to use that array instead of the original. And heck, if I want to now print this thing out, I can do for int I equals 0, I is less than 4, I plus plus. And then inside of this loop, I can print out using printf and %i \n whatever is at list bracket I, which can now go up to index 4. Not through, but up to index 4, because there's 4 possibilities there. And then at the very end of this program, I should probably be a good citizen, so maybe time passes again. But eventually, I should free that list itself. I already freed the temporary, the original list. Now I want to free the new, bigger list as well. And now I can just return successfully 0. All right, if I didn't mess this up, let me open my terminal, do make list again, /list, and I should see 1, 2, 3, 4. And I think this is now correct. But notice that just to make this simple idea, I mean 44 lines of code just to make an array slightly bigger, if you will. And there's actually a subtle bug. This is super subtle, but it's the kind of thing you need to start thinking about whenever you're manipulating memory. And I'll call this one out myself. So notice that at the very beginning of this program, when I initialized space for 3 integers, I realized something could go wrong because list could be null. And OK, I'm going to exit immediately by returning 1. But there's another subtlety here which I didn't fix yet, and Valgrind eventually might catch this for me. Notice here, I again use malloc, and I did realize here, oh shoot, something could go wrong, and malloc could again here return null. So I do check for that. But notice that I return before cleaning up the memory that I already asked for. So this is super subtle, but what I should really do at this second use of malloc is if I didn't have a valid return value for malloc, that's fine, but I had better free the successful value of malloc that I got earlier. Otherwise, this is the definition of a memory leak. If you've allocated memory here, you're exiting your program here, but you never actually give this memory back, like that's a memory leak. And to be fair, the operating system will eventually like reclaim that memory for you, but if we use this as sort of a working principle, you should always, always, always free memory that you yourself have allocated, whether it's in cases of error like this or intentionally like down here. All right, let me go ahead and just make sure I didn't break anything. Make list, /list, and voila, we have now 1, 2, 3, and 4. All right, let me propose that this is not actually as annoying as it needs to be when you want to grow a list of size 3 into a list that's slightly bigger of size 4. There's actually one other function we can introduce today that will make our lives a little easier. Let me go back to VS Code, hide my terminal window, and let me propose that what we could do is actually this. After some time has passed inside of main, instead of allocating a brand new array like this of size 4, we can actually do this instead. We can use a function that we've not seen before called realloc and just ask really C to do the reallocation for me. And this is nice because what C is going to do is if we get lucky and it is not the case that we painted ourselves into a corner, so to speak, and there's no hello world right after the 1, 2, 3, realloc is going to be smart. And if it can leave the 1, the 2, and the 3 in their current locations, but just give you a little more memory to the right of that array, so to speak, realloc is going to do exactly that and give you back the same chunk of, but a slightly bigger version of that memory. So you therefore do not need to move everything around in the computer's memory yourself. Now, in order for realloc to do all of that, we actually do need to tell it what the address is of that original chunk of memory. Yeah. So unlike malloc, which takes only one argument, realloc actually takes 2. The first of which should indeed be the address of the chunk of memory that we are trying to resize. Now, just like malloc, realloc might also return null in the event that maybe not enough memory is available. So we still need to check for that return value, immediately freeing the original list and returning 1 as needed. But what we don't need anymore is this chunk of code here, wherein we were previously copying from the old chunk of memory to the new chunk of memory all of those values, because that too is among the features that realloc provides for us. But my God, I mean, still, like what? Now we're down to like 40 lines of code instead of 44. Like, it's not a huge gain. So is there perhaps a better way to go about this process of actually resizing arrays if and when we need more memory? And yes, now that we have access to pointers from last week, functions like malloc, now realloc as well as free, we can actually build a memory structure, a data structure that doesn't need everything being moved around ever. We can leave everything where we put it in the first place by way of a structure called
yes, I was right. Linked
linked list.
I was
so
right.
What then is a linked list? Well, let me propose that a linked list is a list whereby you're just using pointers to link things together in the computer's memory. So for instance, if here is our canvas of memory, and there's a lot of places that things could end up in this story, suppose that I want to store the number 1 first. Well, that location happens to be available, and so I plop the number 1 there. We know from last week that every byte in a computer can be uniquely addressed. Just like this building is 45 Quincy Street, this is maybe byte number 0x123, using last week's hexadecimal notation. Now, suppose for the sake of discussion that maybe this space is being used, this space is being used, this space is being used, so there's no room at the moment immediately next to this number 1. That's OK. Why don't I go ahead and plop the number 2 where there is room, which is maybe over here? Maybe that location, for the sake of discussion, is 0x456. Where do I put the 3? Well, maybe it ends up over here. And that happens to be location 0x789. So no longer are these 3 integers contiguous, back to back to back. They're sort of all over the place in memory. But that's OK, because if I can somehow connect these dots by pointing one to the other, maybe I can kind of stitch together a data structure in the computer's memory. And I can if we use last week's building block of pointers. Let me waste a little bit of space by using another byte, or technically it might be as many as 8 more bytes. So this is not drawn to scale, but pointers, recall, typically take up 8 bytes or 64 bits nowadays. But I want to draw these things more cleanly as simple rectangles here. So here's still an int. Here's still an int. Here's still an int. But let me propose that if for every integer in this list, let me also allocate a pointer, and a pointer. So each one can point to another location. So what should this pointer point to? Well, ideally, it should point to 0x456. What should this one point to? Ideally, 0x789. What should this point to? Well, if this is the end of the list, we need some kind of special sentinel value. And in the world of memory, like, what's the only sentinel value we've seen thus far that can kind of signify the buck stops here, there's no more list? So null. So 0x0, really. So just arbitrarily, but universally, we decide to use 0 as a special address that just means there are no more numbers in this list, aka null, as we saw last week. Now, this is all fine and good. Memory address, memory address, memory address, and we're stitching things together in this way. But you don't need to think at this low level. Recall from last week, you can think of pointers as, for the sake of discussion like last week, you can think of pointers as really just pointing from one location to another. And so we can kind of abstract this away and just get rid of all of that and use some basic arrows instead. So how do we keep track of a linked list? Well, a linked list of numbers, well, we store the numbers themselves wherever there's space in memory. We use some extra pointers associated with each of those numbers to kind of link us from one to the other. And then the linked list itself, it turns out, we're going to spend one final pointer that just keeps track of where the start of, or the so-called head of the list begins in memory. So what's the upside here? Well, the problem I claim we have solved is we no longer need to have things contiguous, back to back in memory, which means we can make much more efficient use of memory because we don't need a huge chunk of memory to be available all contiguously. Especially if the program's running over time, you can just start plopping things wherever you have room. Now, for those familiar, that actually can lead to something called fragmentation of memory, where your data structure is kind of fragmented all over the place. But nowadays on modern systems, not really a big deal. And these pointers allow us to get from one location to another. But clearly, even in this picture alone, there is a downside. There is a cost for linking numbers together in this way with pointers.
Additional size.
What is the downside of linking them together here? Twice as many? It looks like it's twice as much space, and it frankly might be a little bigger than that if these pointers are particularly large. You're spending space, but you're gaining the flexibility of no longer needing to copy everything from one smaller location to one bigger location. And if you've got lots going on in memory, you can actually use all available memory as opposed to telling the user, sorry, I've got a lot of bytes available, but some are here, some are here, some are here. I just don't have them all contiguous for you. That would be really obnoxious if the program can't proceed because you have enough memory, but it's not all in one place, and you don't want to spend linear time like shuffling everything around. A linked list just gives you flexibility. You can use what memory is available, albeit at the cost of these pointers. So it's not a win-win, but it is a trade-off, depending on what feature is most important to you.
Gotcha.
Now, all right, so let's translate this to the simplest code that we can, and it's actually not all that different from some of the syntax we've seen. Here is how I might remember implementing a couple of weeks back now a person, whereby originally it was a string name and a string number. We took away those training wheels, and we revealed last week that it's char star name and char star number, but this indeed is a person. But this allowed us, using struct and typedef together, to create a new structure in memory that encapsulated information we cared about, like a person's name and number. Well, let me propose today that we actually introduce a new term of art, node. It doesn't really have a technical definition as much as it is just a container for data in memory. So node is very common in graphs and other types of structures, but node is like a generic rectangle that stores some stuff for us. What could I put inside of this data structure in C to implement that concept of a rectangle with both a number and a pointer to another number? Well, I can literally say int number. So inside of every rectangle, aka node, is going to be an integer called number. And then this one's a little weird. I'm also going to store a pointer called next that points to another node. So we've not seen this word node before, but it's the same idea as char star. But instead of pointing to the address of a character, this variable next is going to point to the address of another node. And this is somewhat subtle and a little annoying, but because C reads code top to bottom, left to right, there's a bit of a gotcha here. I am not allowed to use the word node here if it only technically exists once I get to the final line of this code. So a little subtlety in C. There is a fix, though. I didn't need this for person, because persons did not involve linking things together in this way. But if I add the word node here, so it's a little more verbose, typedef struct node, then I can change this to struct node star as well. So now I've seen them top to bottom. This can stay the same. That's the solution to that problem. And this is how everyone does it in C. It's not always necessary, as with persons, but here you just need to mention a little more verbosely what is the name you're giving to this thing so you can reuse it here from top to bottom. So what does this do for us? It just creates in code a definition for those yellow rectangles that we just drew onto the screen. How can we now actually use these? Well, let's take a look at the code via which we can start creating a linked list. Even though at a glance it might seem a little complicated, but it's going to build on exactly what we did last week. So let me go back to VS Code here. Let me actually get rid of pretty much everything we just did, effectively getting rid of our array-based implementation. At the top of my file, let me go ahead and create with typedef and struct and node exactly that data structure that has a number, and inside of that is a struct node star next. And then the name of this thing itself shall be more succinctly node. Just to be clear, we could call node anything we want. We could call it rectangle, if that's simpler. We could call next anything we want. We could call it arrow. So these are just arbitrary but conventional choices to describe that yellow rectangle previously on the screen. All right, now what do I do in my program to create a linked list that looks ultimately a little something like this? Well, first, I'm going to create a pointer that is of type node star called list and set it equal to null. What this means is that I have created on the screen over here the pointer at far left, a single pointer that's pointing to the beginning of this list, but I initialized it to null because there is no list of numbers just yet. All right, what do I then want to do? Well, let me just do something 3 times just for the sake of discussion. Let me do for int I equals 0, I less than 3, I plus plus. But in the real world, this should probably be more dynamic, and I don't just hard code the number 3. But what do I want to do? Well, if I want to achieve this picture, I think what I need to do is ultimately use malloc to create a node, put a number in there, and then do it again for another node, put a number in there, and then do it a 3rd time, put a number in there, and then somehow stitch these things together. So how can I go about doing that? Well, let me propose to do it this way. Inside of this loop, because I want to do this 3 times in total, let me create a pointer called n for node and set it equal to the return value of malloc, whereby I want enough memory to fit the size of a node. So I keep using size of so that the computer can just tell me how much memory I actually need for a node. Recall, as always, malloc returns the address of a chunk of memory. Hence, I must assign it to a pointer. But what is that chunk of memory going to represent? A node. So that's why now, today, I'm using node star instead of char star, because last week I wanted a string of memory, aka char star. This week I want a memory for a node instead. So otherwise, it's behaving the same way. Quick sanity check. So if n equals null, something bad has happened. And so I should just go ahead and return 1 at this point to signify error. And I'll come back to the issue of potentially leaking memory later on. All right, here now, I have the opportunity to actually go into that chunk of memory and give it a number. So how do I do that? Well, recall that if n contains the address of a chunk of memory, just like s was the address of a string, if I want to go to that address, I can do star n. And that goes to the address, to the chunk of memory I just created. If I want to then go inside of that chunk of memory and access specifically something like the number field, as in my struct here, well, I can use the dot operator, which we used in the past. So my dot operator would allow me to do this. Dot number equals, and let's just use getInt to keep things simple today, even though that's from the CS50 library. I can go ahead and set that equal to whatever number the human types in. Now, syntactically, I need to make a little tweak here. Because of order of operations, I want to make super clear that I want to go to that address first, then go inside of that chunk of memory and set the number to whatever the human types in. Then I'm going to go to that same chunk of memory, a little redundantly, I'm going to change its next field to at least be some safe value that I know about, like null. I don't want it to be a garbage value. I want to just create this rectangle in memory and know that there's nothing there just yet. What have I now built in memory? Let's do this a little more slowly, a little more methodically by visualizing what it is we've just built. So at the top of the screen here, we're going to see one line of code at a time. And on the bottom part of the screen, we're going to see what I'm building in memory step by step. The first line of code could be this. Just give me a variable called list that eventually is going to point to this list. I don't like this, though, because it means that it technically contains a garbage value right from the get-go. So who knows where this linked list is in memory? And that's why in my actual code, I said, no, 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 let's not tolerate a garbage value there. Even though this does give me a variable called list, let's initialize that to null so that this isn't pointing to some random location. I'm just going to use blank to indicate that it's null. So this is how I might begin the story of creating this linked list. All right, what was my next line of code that I did? Well, I indeed used malloc to allocate enough memory for the size of a node. I claim that malloc always returns the address of that chunk of memory, so I stored it in a variable called n, for short, for node. So where is that on the screen? That's like getting a variable called n, whose value initially is a garbage value, as any variable is. But as soon as I call malloc, that's like giving me a rectangle of memory over here. And so I just have to change the number field and the next field to be the values I care about. So what did I do after this? Recall here that 1, after doing the assignment from right to left, that effectively means that n points to that chunk of memory. I could use OX123, OX456, but who cares? Let's just use arrows for now to keep things visually more simpler. So this variable n is pointing to that chunk of memory. Then I went to that address, following the arrow, and went inside of that structure. How did I do that? Star n dot number gets 1, and that's like actually changing the number 1 there. And it turns out there's actually a simplification of this. This is not pleasant looking code. It looks cryptic. You have to remember all of the symbols. I bet we could simplify it using that one new piece of syntax today. The arrow operator that I showed on the screen earlier simply means do all of this with the parentheses and the star and the dot, but do it in a way that kind of reads more cleanly from left to right. And it kind of does. If this is n, and you follow the arrow, and you go to number, you get to exactly that location in memory. Start at end, follow the arrow, and voila, you are right at that location in memory for both number and next. So most people would actually use this syntax. So just to be consistent, let me go back quickly to VS Code and just make that subtle change. Instead of parentheses star n dot, let's just say more simply n arrow number, and down here, n arrow next. And that's kind of tightening up the code already. All right, what happens after this? Well, I should probably initialize this next pointer to be some known value so that it's not pointing at some garbage value still. How did I do this? N arrow next equals null, just as you saw a moment ago in VS Code. So Oscar goes away, and that's effectively null now. So this isn't complete. This is now really a newly allocated list of size 1, but notice we haven't updated the original list, so this is actually a step I haven't done yet in code. I think I want to set list equal to n, which sounds a little weird, but if n is an address and list should be an address, all I'm doing is copying whatever the memory address is here, OX something, into list, which is like duplicating the arrow and pointing it from left to right as well. And then, heck, I don't need the temporary node anymore in my story because I've just created the first number in memory. So let's actually go back to VS Code for just a moment and add that final flourish at the bottom of this for loop. When I am ready to insert this node into the list, what I think I'm going to do is I'm going to say list equals n. The problem with this approach at the moment is that if I'm doing this in a loop, I am going to constantly update list to point to the very node I just allocated. So if we keep going through this loop 3 times, I'm going to create a node for 2 and then a node for 3. But based on that line of code, I'm always just going to point list at the most recently created node. And there's going to be no arrows linking the 3 to the 2 to the 1. And so I actually need to be a little more clever about this. And so in VS Code here, what I'm going to do at the bottom of this loop here is instead, I'm going to do the following. I'm going to specify that whatever n's next field is should actually be the same thing as the list. And then I'm going to say the list should point at n. So I technically don't need this line of code here anymore. What instead I'm going to do is this. If I go back to the picture over here, and I create now a second node, let's see what actually happens. If I create a new node here with malloc, and I get some other chunk of memory here, I will eventually want to point n at that, just as I did before, as the same line of code does the second time through my loop. If I want to change that garbage value to the number 2, I go to n, follow the arrow, set it equal to 2. Then I go to n, follow the arrow, set next equal to null. This still isn't a linked list because notice the 1 and the 2 are not yet connected. But the code I just wrote inside of my loop here proposes to update the currently created node n's next field to be that of list, and then update the list itself to point at this new node. So what this means concretely, even though we're crisscrossing some lines here, is the following. If my next step is going to be set list equal to n, as it was a moment ago, that's bad, because watch what happens. If I immediately set list equal to whatever n is, and n is pointing here, that's like doing this. And this is bad, as per the red on the screen. Why? This does not link the list together. Why? Yeah. Yeah, I've like lost track literally of the very first node. In computing speak, I have orphaned the very first node because no one is pointing at it anymore. And this is actually a really bad memory leak, because if you have no variables pointing to that chunk of memory, you literally cannot free it later on in your code. So it's never going to be freed. And you'll just gradually leak more and more and more memory by something as simple as this. And so that's why I indeed deleted that line of code. And I propose now, most recently in VS Code, to do this. Take the new node, follow its arrow, and change its next field to be whatever the list itself is currently pointing at. So what does that mean? Go to n, follow the arrow, and update this box here to be whatever the value of list is. And here again, it's a little weird because I don't want to copy the whole list, but list, L-I-S-T, is just a variable containing a memory address. And that memory address is whatever the address of this first node is. So that's like saying, this box should point to the same thing that list points at, which is like adding an arrow in memory this way. Now, that's not the finished work. There's one last line of code that I did just add to VS Code where now it is safe to update list to equal the address of the new node, because the new node is here pointing at this chunk of memory. So if I set list equal to that address, now we're linking things together. Takes a few steps, and in fact, let's get rid of the temporary memory that I created to make all of this happen. Now I'm creating a linked list. And if we were to go through this one more time around, same exact code inside of that for loop for the third and final time, I would then have this structure, for instance, in memory. Now, I've deliberately, artistically written it sort of left to right, so it kind of flows in a pretty way. But technically, the 3, the 2, the 1 could be all over in the computer's memory, but these arrows would just curve a lot and point to those locations. But I haven't quite built up the same list of numbers as before. I kind of screwed this up. What have I done wrong, it would seem here, vis-a-vis the array that contained these same numbers? Like, that code is correct. It links numbers together, but what have I built in memory that's a little different? Damn it, it's backwards, right? Like, it's 3, 2, 1. If I read it from left to right, which I should, because this is where the start of the list is, the so-called head of the list, and indeed 3 to 2 to 1. Now, technically, I could probably come up with some way of reversing that process, but these arrows literally point in only one direction. And because, in fact, what I've actually built is what computer scientists would call a singly linked list, whereby each node points to another node, but there's no way to go in the other direction. That would be what's called the doubly linked list. And I could do that. I could build rectangles or nodes in memory that have 3 locations, one of which points this way, the other of which points that way. Then I can go back and forth and solve that same problem. But at the moment, without some fancy code, I don't think I can print these numbers from left to right in exactly the same way. So I built this darn thing backwards, it would seem, with this code. So while the code itself is correct, it doesn't maintain the property that I wanted of keeping these things perhaps in order. So what's the implication then, or how do I actually go about recovering from this? Well, let's actually see how the list prints in practice. Let me focus on the slide here. Here's that same memory. Suppose that I give myself a temporary variable. We'll call it pointer for short, which is what a lot of programmers would do when using pointers, PTR. And if I created a variable in memory called pointer, and I initialized it to the first element of the list, I could use printf and print it out. I could then follow that node's own arrow and effectively point at the second location and print its number out. Then I could update that arrow to point to the last location and print its number out. So this idea of having PTR, this variable, loop from left to right, is actually something I could translate pretty readily into code here. In fact, let me do that. In my VS Code here, instead of leaving this as is, let me go outside of this for loop and propose that time passes. Maybe there's some other code that I've written there. But what I really care about now is printing those numbers. So how can I do that? Well, I need to create sort of my, sort of foam finger in the computer's memory, which I'll call PTR. So I can do node star PTR. And I can set that equal initially to, well, how do I begin this? Let me go back to the diagram. I want PTR to point to 3 first, the very first node in the list. So in code, what should I set PTR to equal? How do I access the head of the list?
List.
I don't have too many options when it comes to variables in this program.
The list.
What could I set
the list points to the head
to equal?
Or is the sentinel head?
Well, there's only one variable in the computer's memory that technically points at anything at this point.
List.
So the answer is on line 12.
List. Come on.
List.
Come on,
that's
Harvard.
Correct. So
Come on, Harvard
I could
students.
set PTR equal to
Thought these kids
list
were smart.
because just like this diagram, if I want PTR to start at the point of the to point at the start of the list, that does not mean that I want it to point to this thing. This is just a variable that I'm using to keep track of where the first node is. But again, if we were to take away these arrows as an abstraction, this just contains an address, like OX something. So what I really want to do is put into the PTR variable that I just created the same OX something so that it's pointing at the first node in the list. So that's like saying PTR equals list, semicolon, so that PTR effectively points at that same first element. And again, this is the annoying part of pointers, because they are variables, but they're really addresses to other variables, that kind of thing. So you kind of have to pause sometimes and think about, all right, what is it I'm actually moving around in the computer's memory? In this case, it's just the address of that first node in the linked list. All right, if I go back to VS Code here, the rest of the code is actually fairly straightforward, and we can use, for instance, a while loop. So while that pointer value is not null. So while I still am pointing at valid memory and I have not reached the end of the list, go ahead and print out using printf, %i\n, and print out the current node's number field. So again, PTR, just per this diagram, is pointing at this node, and this node. So in code, what we're going to do is literally dereference PTR with the arrow operator, follow that arrow, get the number field, and print it out. The only bit of complexity now is inside of this while loop, how do I update the arrow to go from one node to the next? Well, this too is a little mind-bending at first, but what I really want PTR to equal the next time through the loop is to point at this node. Well, how do I do that? I think after one iteration, I can set PTR to be the exact same thing as the first node's next field. So if PTR is pointing at this node, well, then PTR arrow next is the address I want, because it points to the second node. So even though this looks a little weird at first glance, this is the canonical way to sort of iterate through a linked list. I just want to set PTR now equal to whatever PTR is now and its next field. So this is just like following the arrow, following the arrow, following the arrow. And if after all of this, I open my terminal window and I do make list again, enter, there is going to be an error.
You didn't include
I promise I knew was coming.
CS50.
But how do I fix this? Undeclared function get int. Kind of need those training wheels back. We just need the CS50 library, and that's fine. I just didn't want to use scanf and like complicate things unnecessarily today. I just wanted to get a simple integer to play this game. So I'm going to include CS50.h at the top, reopen my terminal window, rerun, make list, enter. Now we're good, /list, and I'm going to manually do the exact same thing as I did with the array. 1, 2, 3, enter. It's backwards, but at least it is built up in memory. And we can indeed see that what I have built is exactly this structure here. The upside, though, of having built it backwards is actually arguably a little bit efficient. In fact, what I've actually done here leads us to kind of a discussion of like the running time of these linked lists. Like arrays were super fast because they were contiguous, and we could search them from left to right in linear time. Or per week 0 and 2, if we sorted the elements, we could even achieve logarithmic time, log of n, because we could do binary search again and again and again. But let's consider linked list. Here's kind of our cheat sheet of some common running times, but not all of the running times in the world. How much time does it take right now to search a linked list from left to right for some value?
O of n.
Big O of n. Why is that? Well, you have to start at the start of the list, the head of the list. And if you're looking for any value, whether it's sorted or not, worst case, you might have to go from left to right all the way to the end, aka the tail of the list in this case. So yes, big O of n exactly describes the running time of search. What about insertion? The process of adding a node, adding a node, adding a node. Here's where I actually did something arguably clever, even though it kind of backfired in the sense that things came out backwards. What's the running time, per this cheat sheet, of inserting a new node into the linked list as we've done it so far? It's not O of n. O of n would have implied that we're constantly going from left to right and adding it to the end. But I wasn't adding it to the end. I was adding it to the beginning, which means big O of... It's actually big O of 1, because the beginning of the list is always perfectly accessible to me. It doesn't matter how long the list gets. If it has 3 elements or 300 elements, the start of the list is always right there in front of me via that list variable. Now, technically, it doesn't take literally 1 step. I think if I did the pointer, so I might have to use like 2 or 3 steps in total, but it's constant. And that's what big O of 1 means, constant time. And so, indeed, I can kind of see that here. If this is my list originally and the whole thing is empty, and I insert the number 3, that only took 1 step, really. Or that took, rather, a constant number of steps, whether it's 1 or 2 or 3, whatever. It wasn't n steps. How do I insert the 2? Well, my picture looked briefly like this. That 2 has no dependency on how long the list already is, because I'm just prepending it to the list. And the number 3, prepending it to the list. So even if this thing is getting longer and longer and longer, there's no reason for me to walk or search the thing from left to right. So the upside then of this algorithm thus far of prepending elements is that I can achieve, sure, big O of n for searching, but big O of 1 inserting. And if I'm doing a lot of inserting into this data structure, like that is compelling, as constant time always is. The catch, though, of course, is that things end up backwards if I care about the order in which I insert them. And maybe I do, as per our discussions of stacks and queues, which are fundamentally separate from this topic. Now we're talking about low-level implementation details. But I might have accidentally now created a LIFO structure instead of a FIFO structure, which might indeed be germane. So how can I sort of work around this? Well, maybe I could do something a little differently instead. Instead of prepending, well, let me see how much effort it would be to actually do a maybe an appending to this list instead. So once I build the list with the first node, I ideally plop it here. Second node over there. Third node maybe over there. I can maintain sorted order, which is great if I do in fact care about a FIFO property, because now first one in could be the first one out, because it's always readily accessible. But I think I just shot myself in the foot here. Let me quickly pull up some code for this. And let me propose that my code now might look a little different. Let me open up VS Code here. And in VS Code, let me go ahead and propose that if I want to append instead, that I go ahead and do this. Let me hide my terminal window. Let me scroll down to the bottom here. And I think what's going to have to change is this stuff here. I can't just blindly insert the new element at the start of the list. And that's really what was happening with these 2 lines of code here. So how do I do this? Well, it turns out the code's going to get a little more complicated as a result. First, I'm going to initialize my next field here to null, just to make sure that it's not a garbage value, as I originally did, but then decided, it's not necessary if I'm immediately prepending it to the list. But now I actually have to consider 2 scenarios. And this is where sort of building things in memory gets a little annoying, because you might have corner cases, things that don't happen all of the time, but might sometimes happen. And what's a potential corner case when building a data structure like this? Well, maybe at the very beginning of the process, there is no list. So you can't just blindly append it to something that doesn't exist. You have to kind of special case the start of the process. So what do I mean by that? Well, in code here, I might do this. If my list variable, which keeps track of the whole thing, equals null, as it will at the start of the story when no nodes are in the list, well, this is easy. I'm going to store the address of the new node I just created. So I'm going to put a comment to myself to make clear, if list is empty, I am going to do this special case here. But appending is indeed going to involve some kind of loop. So else, I'm going to go ahead and do this. And I'll add a comment here. If list has numbers already, the second case that I want to handle is going to look a little different. I'm going to iterate from left to right over this structure in the following way. And I won't dwell on this code because it's perhaps more detailed than we need right now. But one way I could do this is as follows.
Wow.
For node star pointer equals list, pointer not equal to null, pointer equals pointer next. Now that's a mouthful, but we'll come back to what that means in just a moment. Inside of this loop, I'm going to say the following. If at end of list, I am going to, so if pointer next equals null, then I am going to assign the next field of this thing equal to n, and then I'm going to break out of this entirely. All right, so this is a mouthful, but what do I actually want to do here? Well, if this is my empty data structure initially, and I want to add 1, that's easy. I just set list equal to 1. But then things get more generalizable for the second, the third, the fourth, the fifth node, because as follows. If I want to insert this next node 2, what I really want to do is start at the beginning of the list, and a moment ago, look for the end of the list. And as soon as I find the end of the list, as indicated by this being null, OK, now I can append it. How do I insert the third element? Well, I start at the beginning of the list. I iterate through it. I look for the null element. And then I can append that to the end of the list. So even though this code, very admittedly, is probably the most complicated that we've seen thus far, it actually achieves that same idea, as per my comments. So if the list variable itself is null, there's no list already. That's a super easy case. Just set list equal to the address of this new node, done. The harder part is every other case where we're appending to the end of the list. Now here I'm using a for loop, which is a convention. I could use a while loop, as I did for printing. But let's just think about what this does. This creates, like any for loop, a variable, in this case called pointer. And it sets it equal initially to the start of the list, because that's where I want my finger to point from left to right. Then I keep doing this so long as the pointer itself is not null. And then on every pass through this loop, just like with my while loop, I want to set pointer equal to pointer next. That's like moving my left span to point to the next node, to the next node, to the next node. And I want to do this so long as the pointer is not null. Because once it is null, then I've gone too far. So how do I do this? Here I am inside of that loop, and I'm asking, if I'm pointing at a node whose next field is null, that means I'm at the end of the list, because that's the 1 node initially, then the 2 node, and so forth. So if the thing I'm pointing at, next field is null, there's nothing more to go. So what do I want to do? I want to change that null value to be the address of the new node. And then I'm just going to hit break and break out of this whole loop because I'm done. So it's a mouthful syntactically, even though we're using all of the same stuff we saw last week, like stars here and now arrows here. But this is just asking the question, as I point from left to right, am I pointing at a null ending of the list? If so, just tack on 1 more node, please. And that's it. And again, if you're comfortable at least with the concept of what we're doing here, appending, that's really the current goal at hand. And in fact, what I can do now is let me go into VS Code here, and I can actually change that version of my printing to be very similar, if it's helpful to see one side by side. So in fact, if instead of using a while loop at the end of this code, as I did before to print this thing out, let me actually change this to be quite similar instead. Let me go in here and say for node star pointer equals list, pointer not equal to null, pointer equals pointer next. And then inside of this loop, just as before, let's just print out %i\n, the number in the current field, semicolon, and then down here, heck, I'll return 0. So in other words, what I did with a for loop is identical conceptually to what I did with a while loop. If I undo, I'm hitting Control Z again and again and again. I'm just undoing all of this code. The exact same thing as this, but just as we saw in week 1, for loops tend to be a little more concise, fewer lines of code than the equivalent while loop. So that's all I'm doing here,
I like while loops
is rewriting this using the same for loop syntax.